It's going well so far. Wish it were Friday, not Wednesday. Hurting right now? Do you have any questions at all before we get started? All right, so we started talking about doing trig functions of acute angles today. We're going to continue that discussion and do another application here problem on that worksheet that I gave you last time. We did a third problem that was on that. Then I'm going to talk about some special angles that we can do the trig functions on, and then we're going to talk about extending this and being able to do the trig function of any angle as opposed to just acute angles. So angles that are larger than 90 degrees, angles that are negative, all those good things. We're going to talk about that starting today. We'll finish that up Friday, and I'm also going to give you a quiz on Friday over the first. The quiz won't cover 6.3. It'll just be the 6.1 and 6.2. The stuff about angles that we did, and then the acute angle trig that we're talking about now. Okay, so we'll do that just as a kind of a preliminary heads up. Your first test is Monday the 10th, so a week from Monday. Just to, like I said, just to give you a little preliminary heads up. It'll cover 6.1 through 6.4. Okay, so like I said, we're starting 6.3 today. So there's just be, after today, there'll just be one more new section before we pass. All right, so let's see if we can set this problem up. See if I can get my glasses out so I can actually see. One of the wonders of getting older. Reading glasses have to come out. All right. In this particular problem, we've got a flagpole that casts a 42-foot shadow. It talks about the elevation, the angle of elevation to the sun, and it wants to know what the height of the flagpole is. So I'm going to assume that the flagpole is perpendicular to the ground. Ooh, hey. Otherwise, I'm going to have a really hard time doing this problem. Right? So the way I've got this drawn right now, what part's corresponding to the shadow? The bottom, right? So I know that this side is 42, correct?
Yeah,
Because that's the shadow part. This is the part that I'm looking for, not flagpole. Okay. All right. So the angle, the last part we need is the angle, right? So this is the angle of elevation piece that this is talking about. So as we start from the tip of the shadow and up to the sun, that angle has to be the 57.4. Okay. All right, so just in general, a couple of things that you want to make sure that you're aware of if you're working on these type of application problems. If I am on the ground, then the angle up this way is your angle of elevation. And I think we're probably all okay with that one. The one that gets a little bit dicier, if you will, and you have to make sure you pay attention to it, is the angle of depression. So if your ground is down here and you're above the ground and looking downward, ooh, hey, if this is you and you're looking downward, then you've got to put in a kind of a line of sight idea, and this angle is the angle of depression. Okay? What'll get students confused, or at least in my experience what gets students confused, is that you get everything else set up in your picture right, and you'll draw your right triangle, which you need to do, and then they'll use this for the angle of depression instead, which is not right. Okay? The angle of depression is if you were looking straight out from where you are, how far down you have to look So it's that distance, or that angle this way. Okay. It's one of those, be careful when you read the problem, make sure you get the angle labeled right. Okay. Now it turns out, of course, that you really are able to get an angle from the triangle, because this has to add up to 90, so this would just be the complement of this angle. Or, if you remember stuff from parallel lines from geometry, this angle has to be the same as this angle here. A couple of ways to get at it. But I want to make sure that I mention that angle of depression idea, because it'll pop up. You'll see a couple of them in the worksheet that I gave you as well as you're practicing those. But you might see it on application problems later as well. So just make sure that you've got the angle labeled correctly. I mean, it's not as important in this particular problem, but in general, you might need to know that. All right. So now that we've got the triangle set up, we okay with this setup for this particular problem here? All right, so now we need to figure out a trig function that relates this side, right, and the other two pieces of information that were given. So what trig function do we want to use? The tangent, right? So, in fact, what would the equation be if we use tangent? But what will the equation be if we use the tangent? What will
Opposite over adjacent.
Okay, so opposite over adjacent. So setting up the equation, you would have what?
Opposite over 42.
Okay, so you have x over 4. Oh, I have that in red, sorry. X over 42, what does that have to equal? The tangent of the angle, the 57.4 degrees, right? Good, you multiply the 42 on both sides. This problem says nearest tenth of a foot. So if you put that in your calculator to the nearest tenth, what do you get? 65.7, is that what you said?
Yeah.
Okay. And that'll be feet. We okay with that one? Now I'll post solutions to the rest of these on Moodle so you can see them if you've got questions. A couple of them are a little trickier than the others. Just to kind of give you a heads up, but they're all the same idea, right? Get your right triangle set up, get an equation involving one of the trig functions set up so that you can solve for the variable that you need. Now again, as you're going forward with problems, make sure with your calculators you guys set it to the right mode, either radians or degree mode. We're going to start doing more and more stuff with radians as we go along. So you'll want to have things set in radian mode. But because of the way application problems work, a lot of things are stated in degrees, so you'll need to switch back and forth between them. Okay, just as another heads up kind of idea. All right. Questions on any of that at all? Before I go on to other stuff? All right. So let's talk about some special angles, if you will. And we've already talked about these triangles to start with. And we're going to refer back to these triangles even when we're going to start talking about trig functions of angles that aren't acute. We're going to come back to these same triangles more and more and more as we go along. So we talked about a couple of these special triangles the other day. We had the 30, 60, 90 triangle, right? And we had the 45, 45, 90 triangle. These are going to be helpful for us to be able to do the trig functions of 30-degree angles, 45-degree angles, and 60-degree angles. Or things that look like those particular types of angles as we go forward. So we need to remember what the sides look like. And it's just, you can do them with fractions if you really want to, but I try to avoid the fractions on the sides. We said that if this side was length 1 for the 30, 60, 90 triangle, what was the length of the hypotenuse? Oh, there is a root 3. That one's down here, right? This one's 2, yeah. Good. So some of the language they use in geometry This one's typically, for a 30, 60, 90 triangle, this one's typically called the short leg. This one's called the long leg. Okay? So your hypotenuse is twice the length of your shorter leg. The longer leg is square root of 3 times the shorter leg. But how can we use this now to get what we refer to as the exact values of these trig functions? So for example, if I asked you for the exact value of sine of 30 degrees, what would you tell me? Well, how do you get the sine in a right triangle? Opposite over adjacent. Or opposite over hypotenuse? Sorry, what's the opposite? 1. It'd be 1, and the hypotenuse is 2, right? So we'd have a half. Right? What if you wanted cosine of 30 degrees? So cosine is adjacent over hypotenuse, right? So you would get square root of 3 over 2. Everybody see where we're getting those numbers, right? Again, for our sine, we're doing opposite over hypotenuse. For cosine, we're doing adjacent over hypotenuse. Right? Don't need a calculator for these. We have the exact values, and I am going to expect you to know these exact values for these special angles. Don't think it's going to go away, because it won't. Okay. What about tangent? One over square root of 3. Good. Yeah, that's right. And I do not care if you rationalize the denominator. I'm a big boy. I can handle square roots in my denominator. It's fine. Okay. The act of rationalizing is an important skill. The act of trying to get a radical out of the denominator because simply the radicals in the denominator is stupid. Okay? I don't care if you rationalize denominators at all. Don't waste your time. Okay? Your calculators will do it for you. So many of them will do it now anyway. So again, the process of rationalizing is an important skill because you see that pop up we're actually going to see it later on in the semester, being able to rationalize. But sometimes you want to rationalize a numerator because that's what you need to do to be able to see how to simplify the problem. Okay? So the fact that a square root is in the denominator, no big deal. Okay? One of the reasons why it was such a big deal was because before calculators, it was hard to divide by a square root if you're trying to get a numeric approximation. So if you rationalize, then you're dividing by an integer, which is a little bit easier to do, obviously. But that's really old school, and don't need to worry about it anymore. All right. So we can get those exact values. And again, these are ones that you need to remember. Of course, I really don't have to memorize tangent, because we've already talked about how can I write tangent in terms of sines and cosines. What is tangent equal to in terms of sines and cosines? Well, in terms of the actual functions, though, what is it equal to?
Sine over cosine.
It's sine over cosine, right? So if you remember sine and you remember cosine, you can figure out tangent, right? I don't need to memorize the tangent values. I can figure it out from the sine and the cosine. So really, you just need to know what sine and cosine are. And if you remember the triangle, you don't even really need to remember you don't really even need to memorize the values. You can read it from the triangle, right? So where those 30, 60, 90 triangles and the 45, 45, 90 triangles come out nice for you because you don't have to memorize them. All right. What if we wanted to do and of course, you could do the secant, cosecant, and cotangent by taking the reciprocals, right? If you wanted cosecant of 30 degrees, what's the cosecant the reciprocal of? Well, it's in general, just what function is it the reciprocal of? Sine. And so in this case, it would be 2, right? If you wanted secant of 30 degrees, what's it the reciprocal of? The cosine. So it would be 2 over the square root of 3. And if you wanted cotangent of 30 degrees, what's it the reciprocal of? Tangent. So you would have root 3. Does that make sense? What if we did the 60-degree angle instead? If I want sine of 60 degrees. Do I need to change triangles? No. It's the same 30, 60, 90 triangle, right? This one over here. What's the sine of 60 degrees going to be? Root 3 over 2, good. Because that's opposite over hypotenuse, right? For the 60-degree angle up here, for this one up here, notice that the opposite side is at square root of 3, right? That makes sense? Okay. All right. What about cosine of 60 degrees then? Yeah, so it'd be 1 over 2, well, 1/2. All right, because again, the 1 here would be the adjacent side. Tangent? Yeah, it'd be root 3 over 1, right? Because it would be the opposite over the adjacent. Everybody seeing where those are coming from? Now's the time to ask if you don't see where they're coming from. Okay with those? Okay. All right, so notice a couple of things. We've talked about this before and why we have these different names. Notice that your sine of 30 and cosine of 60 are the same. All right, the sine of an angle is the cosine of its complement. All right, and vice versa. Cosine of 30 is the same as sine of 60. It's that co-function idea. Let's do the 45, 45, 90 triangle here up here. So what were the side lengths for that one? How did we label the sides for that one? Yeah, 1 square root of 2. Remember that we get to pick the value because we can think about similar triangles. But we know that this is an isosceles triangle. Why do we know that these are the same side? What tells us that they were the same side? The angles were the same, right? So that was, if I call one of them 1, the other one has to be 1, right? And then we can figure out the hypotenuse by using what? Pythagorean theorem. Good. You were listening to me. That's wonderful. All right. So let's talk about the values. I'm going to have to scroll that off the screen. I'll just redraw the triangle. So it's sine of 45 degrees. What'd you get? 1 over square root of 2. Right? And if we did cosine of 45 degrees, 1 over square root of 2 is the same value, right? Which is not a surprise because the legs have the same length, right? Opposite and adjacent are essentially the same, which also makes your tangent equal to what then? 1. Good. Everybody see where those are coming from? Very happy? Everybody quiet? Okay, wonderful. All right. So these are the kind of the special angles, if you will, for needing to know what you have the sine, the cosine, the tangent. And then, of course, you should be able to do secant, cosecant, and cotangent. Right? If nothing else, just remember that reciprocal relationship because you have to remember it anyway. All right? Well, what will secant and cosecant be here for 45 degrees? It'd just be square root of 2, right? Because it's just the reciprocal. And then cotangent, of course, will be 1. Good. All right. All right, so those were for degrees. Now, we also want to start doing things with radians. So one of the things that you should remember and start moving over to radians, especially for one of the ideas that we're going to talk about here later today. Let's think about these angles all in terms of radians. So your 30 degrees, what do you do to change from degrees to radians? Multiply by the pi over 180. In that case, if I had 30 over 180, that'll be pi over 6. Good. Okay, good. And pi over 3. So if you see sine of pi over 6, then you should be able to tell me it's 1/2, and so on down the line. So for example, if I asked you for, say, secant of pi over 3, what would you tell me that is? Well, even if you can't say it off the top of your head, that's fine. Let's think about it in terms of sines and cosines. How could I rewrite secant in terms of sines and cosines? What would that be? The 1 over cosine, right? Right? Secant and cosine are reciprocals of each other, yes? Okay. And then pi over 3 is the same as what angle? 60. And what did we say the cosine of 60 was? It'd be the 1/2, right? Okay. So cosine of pi over 3 is 1/2, and 1 over 1/2 is equal to 2. Yeah. It just says take the reciprocal of 1/2. This is what I mean by I expect you to know what sine and cosine are for these 30, the 45, the 60, the pi over 6, pi over 4, pi over 3. And you'll definitely be expected to remember that for calc. Trust me. I know the professor. She'll expect you to do it. Okay? So, I don't get my wife. I know that she'll definitely expect you to do it. But you don't have to memorize all the secant and the cosecant of all these special angles because you can change them to sine and cosine. If you forget, just change it to sine and cosine. Okay? And you can figure it out from there. By knowing 30, by knowing 45, and by knowing 60 for sine and cosine, you can figure out almost every other problem you'll ever have to do. Okay. Questions on those at all? All right. So let's talk about how we use this then to move up to doing this for any angle rather than just acute angles. So 6.3 is trig functions of any angle, I believe is the title in Hawks, but that's what we're doing. Okay. All right, so we haven't worried as much about putting an angle in standard position because we said that when we're doing acute angles, if we put it in standard position, it's just going to end up in quadrant 1 anyway, right? Now is when we really need to start worrying about standard position because what we're really going to be interested in is where does the terminal side land. So to motivate this by example, let's say you were asked to find the exact value of, let's say, cosine of 2 pi over 3. All right, so I purposely gave you something in radians to start with. Okay, that's right. That's exactly right. It is 120 degrees. All right, so let's think about putting this in standard position. Let's see where this ends up. All right, so this would be your initial side has to be along the positive x-axis, right? The initial side is always on the positive x-axis. That's standard position. We know that, just to talk about this for a second, I'm going to erase this line here in a second, but we know that all the way around is what? 2 pi, right? So if I get rid of that, maybe, halfway around is 1/8 or pi, right? Okay. I'm talking about this because I got to figure out where 2 pi over 3 ends up, right? So pi is 3 pi over 3, right? If I think about common denominator idea, pi is 3 pi over 3, right? So my terminal side is not going to make it all the way here, is what I'm saying, right? I'm not going to rotate all the way to here, okay? However, if I only go 1 pi over 3, well, how far is it to here? How far is that to the y-axis? That's pi over 2, right? Is pi over 3 less than pi over 2 or greater than pi over 2? It's less, right? So I can't stop here, over here, up in the first quadrant, right? So my terminal side must be here. So it must be this angle, that's 2 pi over 3. By the way, why did I know to rotate up as opposed to rotate down? It's positive, right? If it were negative, I would have to rotate down, correct? We agree? Okay. All right. So I want to figure out what the exact value of this cosine of 2 pi over 3 is. So what we're going to do here is we're going to draw what's referred to as a reference triangle. I'm going to make a right triangle and label some sides. Okay? So here's how you make your reference triangle. You always go from the terminal side and drop it perpendicular to the x-axis. All right? So we're going to create a reference triangle by dropping a perpendicular from the terminal side to the x-axis. Always to the x-axis, not to the y-axis, by the way. Drop it to the x-axis. Now, why did I do that? Well, notice here I've made a right triangle. And we're going to use this right triangle to give me the values for the cosine of this particular angle, or whatever values that I want. So the first thing I want to ask is, well, if this angle here, if this angle that we drew here is 2 pi over 3, what does this angle right here have to be? It has to be the pi over 3, right? We agree? Okay. So we actually refer to pi over 3. This is called the reference angle. For 2 pi over 3. Okay? The reference angle is always going to be an acute angle. Okay? Your reference angle is always going to be an acute angle. And we're going to use that acute angle to help us get the trig function that we need. Okay? All right. So notice how we got that reference angle. What did we do? It's what's sharing this terminal side, right? Okay. It's not this one up here. Okay. It's the one that's making up the rest. Basically, it's making up the rest of the half circle. See what I'm saying? It's making up the rest of that half circle in there. Okay. So that's the reference angle in this case. Okay. All right. So why do we like reference angles? Well, we already know what the cosine of pi over 3 is, right? Would you tell me the cosine of pi over 3 is? Yeah, 60 degrees, so that will be 1/2, right? Okay. We already know that, correct? So what this tells me that the cosine of 2 pi over 3 is either, that's a 3, is either 1/2 or it's negative 1/2. It has the same absolute value. Now, we have to pick which one's the correct one. Okay, and I'm going to talk about this in a second. But this is why reference angles are important. I have to determine the sign, the SIGN, whether it's positive or negative. Okay? But the absolute value, the 1/2 piece, is right. I know it's 1/2 or it's negative 1/2. Because the cosine of the reference angle is 1/2. The cosine of the angle I want has 1/2 in it. Okay? Now I have to determine, is it positive 1/2 or is it negative 1/2? Okay? And this is how we do this. And this is why the standard position is important. Okay? When we do cosine, do we use the opposite side or the adjacent side? The adjacent, right? This is the adjacent side for this triangle, isn't it? right? Now think about it as coordinates. If I look at this point right here, does that have a positive? If I think about the distance, is that a positive x coordinate or a negative x coordinate? It's negative, right? So what do you think we're going to use here? Negative, good. All right. So what we say here is since the terminal side is in quadrant 2, oops, the cosine of 2 pi over 3 is negative 1/2. And we're done. No fancy memorizing. If you've seen trig before and did unit circle, I don't do unit circle. Yes?
Can you explain why cosine of this one is always going to be the same?
So the reason why is because if I'm using this reference triangle, so I'm using this angle as giving me the cosine. So or you mean the value? You mean the why this is the 1/2 and the 1/2 is always the same?
I mean, why is the cosine of a reference with a near acute reference angle always going to be the same as the cosine of the altitude?
Okay, so if we're going to go through a lot of that, all right. So if we think about the angle being drawn over here, if we think about this angle, this particular angle here, we know that this triangle, we can make that right triangle, and I get the cosine has to be that one, right? So this, when we did this for, well, cosine in particular, we said that this was adjacent and opposite here, right? And we did the cosine of that angle was that, right? I do mean hypotenuse. Why am I writing opposite? Thank you. I do. I absolutely do mean hypotenuse. Thank you. Okay. So notice that I can think, if I really, really, really want to, I can pick whatever my hypotenuse is, right? Let's make it 1. Right? So then this coordinate here, this x coordinate, is the length of your adjacent side. And of course it's 0 for the y coordinate because I put it on the x-axis, right? Okay. Now just rotate this the rest of the way around. If I do this here, my adjacent side flips to the other side. So I can define it this way, that the point here, that x coordinate has to be the cosine of theta. So the definition of the cosine really is the x coordinate where it hits. That's the technical definition of the cosine, is if I take this point, if I take this length of 1 and drop this down and make the x coordinate, that coordinate is cosine. And so this angle here makes up that rest of that. That's why it works that way. Did that help? No? Okay. Do you see that this coordinate here is the cosine of theta here? Okay. All I've done is do it. I'm just saying I'm going to define it this way now. So let me try one more picture. Okay. Here's theta, and I'm going to make this have length 1. Okay. I'm going to force it to be 1. Okay. The coordinates, by definition, so if this is x and y up here, that is the definition of sine and cosine in terms of where that point is.
I guess the one thing you want is how, from a ratio perspective, how cosine of the one angle is the same. Not, like, I understand where sine and cosine, like, this is a little bit refreshing.
Yeah.
This is all kind of like going back.
Okay, good. Okay, cool.
I'm still not 100% sure why cosine of some angle of any rate would be the same cosine of the complementary angle, right?
Okay, it's not always, well, for cosine it is. In general, it's, the way we're using, let me try it this way. The way we're using the reference triangle again is, okay, if I know that if this coordinate is my x, y, when I put this down here, this coordinate has to be x0. Right, so yeah, the cosine, exactly. So if this angle here and this angle here make up 180. Right? So, but I don't use, for this reference triangle, I wouldn't use the negative for the x because it's an acute angle. That's not in standard position, right? So the reason why I have to pay attention to what the sign is, whether it's positive or negative, is because for an acute angle, it's always positive. But what we're doing here when we're dropping down this perpendicular is we're making up the rest of the angle, the rest of the 180. And noticing that the x-coordinate doesn't change, so the cosine is the same. The absolute value of the cosine is the same. That's where it's coming from. Does that make more sense? Okay. Yeah, you're welcome. I'm happy to get there. All right. Yeah, you'll get 120. Yeah, if you do cosine of 120, you get negative a half. Yep, that's right. Yep. All right, let's do another one. Phew, it was a long way to get in there. That's okay. I'm happy to explain because I don't like it when it doesn't make sense. I want to make sure that we are all on the same page. All right, let's see when we do another one. Let's say I wanted you to find the exact value of, let's do, how about sine of 5 pi over 4? One of the nice things about radians, especially when you're writing them as multiples of pi over something, is that the reference angle turns out to be really easy to figure out for radians. For degrees, it's a little more difficult. You actually have to do some subtraction. For radians, it's easy. If you've already got it written down as pi over something. Notice up here, the reference angle for 2 pi over 3 was just pi over 3?
Yeah,
right? How do we know? Okay, so 2 pi over 3, you're okay with how I got this terminal side? Yeah. So if I go all the way to the other x-axis, the negative x-axis, that's pi. Yeah. So the 2 pi over 3 plus the pi over 3 gives me the pi. So it's the piece that's there. Okay. All right. So let's look at this one. Where does 5 pi over 4 end up? So all the way around here is pi, right? Which is 4 pi over 4, right? So I got to go another pi over 4 to get where the terminal side is. All right, so here's standard position, right? So there is pi, which is 4 pi over 4, right? So I got to go one more pi over 4. Does that make sense? Okay, cool, good. Thank you for stopping me and asking questions. I really do appreciate it, absolutely, because I want to make sure that I'm making sense. Because sometimes I don't. It happens. All right, so is that?
We need a strong, not really strong background, but a unit circle.
I don't ever use the unit circle, ever. I don't use the unit circle. Hmm? This is just counting an angle, right? This is standard position. So there is pi.
Yeah, but on the unit circle, that's over pi.
Yeah, you're right. That's the same angle on the unit circle. I just don't ever use it. Oh, no. Yeah, yeah. All right, and then another pi over 4 is here, right? So that ends up there. There's your 5 pi over 4. The reason why I don't use the unit circle from a teaching perspective is because students will try to memorize absolutely everything all the way around it, and will take the backside of their test, they'll turn it over and spend 15 minutes trying to recreate their unit circle and waste, a quarter to a third of their test time to try to recreate the unit circle, as opposed to just doing the problems. That's why I don't do it. Yeah. Yeah. All right. So are we okay with where that landed? Okay. So we do the reference triangle in the same way. We take from the terminal side, we go perpendicular to the x-axis and make a right triangle. How big is this angle right here then? It's pi over 4. And think about how we got that, which is exactly what I said, right? Rotate to here is pi, and put another pi over 4. Right? So the reference angle ends up being pi over 4. Okay? That makes sense? Where I'm getting that from? The reference angle is just that piece right there that's between the terminal side and the x-axis that it's closest to. Right? That's all the reference angle is you go from terminal side to whatever whichever way to get to the x-axis is closest. In this case, it's the negative side, right? Okay? All right. So what this tells me is that the sine of 5 pi over 4 is the same as the sine of pi over 4, with the exception of whether or not it's positive or negative. Right? Yeah.
How are you going to know which instances to use that the cosine will be the same or the sine will be the same?
They're always the same. Always, either. Yeah, both of them are the same. Yeah. Yeah, they're always the same except whether it's plus or minus. It's always
personal preference, or whatever you have in this form.
Well, okay, you're ready to understand the question. Ask me the question again.
So in the last problem, you said that we know the cosine and cosine of the two angles are going to be the same, with the exception of positive.
Right.
This one you said that it's sine and sine.
Okay, yeah, so it's whatever you're going for. Yeah, I wanted the exact value of sine, so it's the sine that I'm interested in. Yeah. Yep. So I'm not making a choice, I'm actually just using the same function. Yeah. Okay. All right. So it's the exception of whether it's positive or negative. It's the only thing you have to worry about. So what is sine of pi over 4? 1 over square root of 2. So sine of pi over 4 will be 1 over square root of 2. Now we have to make the decision, is it plus or is it minus? Okay? So let's think about it again. Here's my pi over 4. Sine is opposite over hypotenuse, right? The hypotenuse, think of the hypotenuse as a distance. It's always positive, okay? Opposite here is going to be, if I think about it as a coordinate, the opposite is going to be negative, right? It's below the x-axis. So this will be negative. Okay, so we think about it as the opposite side of that y-coordinate in this case. Does that make sense? Yes?
If we change the answer to where there's no square root in the denominator, is that okay?
Oh yeah, you can write square root of 2 over 2. That's fine. I'm okay with that.
How'd you automatically know that sine 5 over 4 was negative 1 over?
Well, I knew, I erased that part. I knew 1/2, or excuse me, not 1/2, 1 over root 2 was from that part, right? So that was how I knew automatically. There was the reference angle is pi over 4, 45 degrees. Sine of that is 1 over root 2. That's how I knew that part, okay? I put in the negative because this side makes this, this terminal side makes this opposite side below the x-axis. That's how I knew it was negative. So it's 2 steps, right? First is I need the reference angle to tell me the value, and then I need to know where the terminal side is to give me the sign, whether it's positive or negative. Does that make sense? Let's do one more, and then we'll do more of these on Friday. Let's say I wanted to do find the exact value. Let's do 1 in degrees here, just for of, let's see, I want to do tangent of negative, let's say, 300 degrees. So the first thing that I need to do, at least in my mind, the first thing that I do is figure out where I am, what quadrant am I in, so I can get my reference triangle drawn. Okay? Now this one, they give it to us in degrees, and it's also negative. So if I start over here, do I go up or go down? I gotta go down, right? I gotta start rotating this way. I hit the y-axis. How many degrees is that? Okay. 180. 270. I've got to go another 30, right? So here's your negative 300. Okay. We agree? All right, so then we take this and drop it perpendicular to the x-axis. Here's my reference angle. How big is that? It's 60 degrees, or we pi over 3, right? Okay. But it's 60 degrees, right? Notice that this is what I was just mentioning about reference angles, by the way. I had to do some arithmetic to get that 60, didn't I? But look at the previous two examples with radians. What was the reference angle for 2 pi over 3? Pi over 3. What was the reference angle for 5 pi over 4? Pi over 4. Right? It's just the pi over what, the reference angle is always just the pi over whatever for radians. As long as you have a reduced fraction, right? I wouldn't want something like 15 pi over 6, because I could cancel out a factor of 3, okay? But in general, when you're doing the radians, the reference angle is just pi over whatever it is. You just ignore the constant that's on the top. That makes it a lot easier to figure out what the reference angle is, right? This one we had to do some arithmetic. But it's the same idea, though. So when I do the tangent of negative 300, I want the tangent of 60. What is tangent of 60? It's root 3. Okay? And then I have to determine, is it positive root 3 or is it negative root 3? Well, in this case, it's positive, mainly because we landed in quadrant 1, right? But notice that your opposite and your adjacent are both positive here, right? So your tangent of 300, or tangent of negative 300, then is also square root of 3. And it's positive since we're in quadrant 1. Oops, let me write it that way. Okay, that makes sense? We're going to do more of these on Friday. Also, we'll do a quiz, a short quiz at the end of class on Friday as well. So, have a good one. We'll see you then. Right. Oh, I'm just going common denominator idea, right? So if I have pi, I can think about multiplying that by 4 over 4. What you were doing, like common denominator things when you were adding. So that's what I mean. I'm only saying that so that I can figure out where the 5 pi over 4 is. I'm trying to figure out where I end up.
So what you do? What you add another power?
So yeah, since I want 5 pi over 4, if I go all the way to here, that's pi. That's really 4 pi over 4s. So I got to go 1 more to get to where the 5 pi over 4 is.
Okay. Wait.
Okay. How about I do it this way? Here's pi over 4, right? Okay.
You deserve something.
This would be another one. So that's 2 pi over 4, then there would be another one.
Okay.
Yeah, that help?
Yeah.
Okay. Oops.